Whatever means he didn't forget. No, I actually forgot. I left him at 6:30 and I think should never leave. And then go. I think hardly. It's okay, Brian.
Okay, so just kind of messing with Zoom right now, but yeah, so we have a test next Tuesday, and so we can cover any questions. One more lecture today that will I think help out in the problem section and that type of thing. So I do want to ask, has anyone attempted to join my office hours on Monday or Wednesday? I start my personal Zoom session, which has a link in Moodle, and I want to make sure that that is working. Okay, so yeah, I've gotten a few questions about the test, more of yeah, the format of the test and that type of thing. So there's been some requests to have a formula sheet or a make it open book or these type of things, and I'd rather stick with the approach that I've outlined and I've used in the past for these type of things, where I provide formulas you need for the exam. I'll be available during the exam in case I forget to put a formula on there or something like that, and I'll assess that in real time, and we'll provide those formulas. I do expect, though, that you have learned how to use the formulas, how to work with them. So you may need to choose which formula to use and how to apply it. But you should not really need to memorize a lot of formulas. There's obviously content that you need to have learned throughout this, and you'll notice if you go through that test preview that we did previously, that there's some things I'm not asking you about. I'm not asking you about the low pass equivalent representation of a single signal. We went through that derivation early on in the course. We have not actually used and applied it yet. So I'm not gonna test you on that. So sure, it'd be nice if you knew every word that I've spoken during this class period, but I think that's unrealistic. It's in your brain somewhere, and if you go into this field, you'll be able to retrieve that information and work with it. But for now, I've outlined what I believe is important at this point of the test of the class, and so I encourage you to focus on that. The test will be drawn from those previews I provided that don't anticipate any surprises or anything like that. So yeah, and I have Monday off from work. As you know, I'm an adjunct. I used to teach professionally for a few years, but now I'm professional engineer, and so it's difficult to juggle all the time sometimes, but we do have a holiday on Monday, and so I can be available for questions and that type of thing then, or if you need help. You guys are seniors, you know how to study by now and prepare for tests and that type of thing. So yeah, I'm retiring at the end of this month, so I'll still do some consulting with my company in March, but things should get a lot easier, and I'll be more available to you. But I do encourage you, if you're struggling to really understand anything at all, definitely set up a time with me, and we'll do a help session, tutoring session over Zoom, and get you where you need to go. So, are there any particular questions on any of the topics that we outlined for the exam? Anything that you feel we need to go over at this point, or on the homework? I do have yeah, I know we went through the homework pretty quick on Tuesday, I guess it was, but hopefully you had already spent a lot of time with the homework and have had a chance to review that homework since then. Okay, I'm gonna jump into the lecture here then, and let's see if I can't get that share my screen again. Zoom wants to put that menu bar in the exact wrong place. Okay, you're seeing my lecture 9 receiver design part 3 right now?
Yep.
Okay, great. All right, so we can circle back to homework review if we need to, or if we have time at the end. But we'll look at equal probable or probably binary signaling error rate. Now we've started on this, and we will look at it a little bit deeper this time with another example. In the last or previously, we looked at antipodal equiprobable binary antipodal binary signaling, and where the constellation was spread out over the real line, the real axis. And then we noted that if it's not equiprobable, that your decision area compensates for that probability of which message was sent. But when it's equiprobable, then you're pretty much dividing it right in two. So we've looked at a few cases like that. So yeah, equiprobable signals yield two decision areas separated by the normal bisection of the line that connects S1 and S2. Right. So do we need to kind of clarify that and talk about that more? We drew a drawing at one point that
Charles, you shifted to.
Oh, sorry.
that looked we drew out some arbitrary points and noted, I guess I ought to move my coffee cup that's in the shadow, it's creating a shadow. And we drew lines connecting these guys here. And then we noted that the optimal decision regions for equiprobable signaling bisects these lines at normal areas. So bisecting is halfway in between and normal right there. So you would draw a number of lines here that are bisecting, and they will I'm a terrible drawer, so they will create or outline your decision areas, right? So if that's a simple binary antipodal signaling scheme, then we draw a line connecting the two, and then we look, okay, that's about halfway in between each other, and we draw a normal line there, right? It's perpendicular. And then if this is S1, this is S2, then this becomes a decision region for S1, and this becomes a decision region for S2. if we receive a signal R out here, we're going to conclude that that's in decision area 2. So it must have been, or it probably was sent. S2 was probably the signal that was sent, right? Because the received signal landed in decision area 2. So if in reality it was S1 that was sent, then we note that this was received in error, right? Because our receiver is going to measure the amplitude right there, and it's going to look at it, and we can draw a vector there from the origin, and so it's going to have some real imaginary value associated with it. It's perturbed by noise and other impairments, right? So it's not lining up exactly on these constellation points, but all the receiver knows is that it's received a particular value that it's measured, and that if it's has a real part greater than this point here, 0, then it's going to conclude that S2 sent it. If it's less than that, it's going to conclude that S1 sent it. At this level, that receiver, that's all it knows, right? So anything other than that is we're going to classify as an error, right? So let me share my screen again. So our probability of error, if S1 is sent, is equal to the probability of error if S2 is sent, because they're equiprobable, right? So we really just need to calculate one. Well, they're equiprobable, and we have we're focusing on additive white Gaussian noise type of thing. So there's no real bias in that noise. All right. So assume S1 was sent, then the error means that the symbol was received in decision area 2, right? If it was received in decision area 1, then that would not be an error, right? We'd be happy in that case. So, and as I drew, the symbol does not necessarily lie on a connecting line, right? So we're going to measure this amplitude in real and imaginary terms. We don't really need to, in this simplified case, measure the imaginary part, because we can simply look at the real part and know whether it lies in decision area 1 or 2. But in general, we need to measure it in a complex domain, and the noise will operate it on a complex domain.
Professor, quick question.
Yes.
We have a quick.
Could you go back to the last slide? Because I just have a question. So the last line, it says the symbol does not necessarily lie in the connecting line. What connecting line are you talking about?
That would be like this line here that connects to right. So don't think that the receive signal is just going to be there. It can be anywhere in this complex plane space, right? So for this case, it's not a big deal, but if you have a more complicated case like this, now we're in the real imaginary plane, and we've looked at a lot of constellations that are more involve complex signals, right? So not any more complicated than that. All right, so now let's
Yeah, should we have one more question? Sorry.
Sure.
Oh, Professor?
Yes, go ahead.
We have one more question.
Go ahead.
If you go back to the drawing that you did, you said that it doesn't matter where the received signal is as long as it's in the decision area, right? So what if we have another symbol that is actually at that area, but which is not the symbol that we're looking for?
Do you mean, so, a more complex constellation,
Just
let's
like,
say? Something like
yeah,
this, right? So now, you would, figure out your decision areas. And here's the, if we're assuming they're equal probable, then, we would draw line bisecting this one, line connecting, bisecting this one. They happen to line top each other, and also this line here. So if this is S1, S2, S3, S4, and we'd probably gray code that, right? But then this would be decision area 1. And this would be decision area 2. And this would be decision area 3 and decision area 4. So wherever your received vector lies, it's going to map into one of those decision areas. And based upon which decision area you land in, now you conclude that was the corresponding symbol was the one actually sent. You may be wrong, but you conclude that. You draw these decision areas so that the entire space is covered, right? So this is going to go on to, infinity. If you measure something way out here, you're going to associate with decision 4, right? So,
Professor, what if it lands on one of the bisecting lines? Is that a special condition?
then basically the rule is you just flip a coin. Now your receiver's just going to make a decision. The likelihood is extraordinarily small, and you just hope for the best, right? So that's, in all these cases, we can apply some more advanced techniques that will, it's kind of like parity checks that you may have looked at in your original digital logic course, or in embedded systems or computer organization design. Hopefully somewhere you looked at the idea of parity check. So we can use those type of concepts and get very, very sophisticated at trying to detect and even correct for errors at the receiver using what we call forward error correction. But we'll touch on that later on in the semester. But yeah, if it just lies right on the border of a decision area, then you just pick one. So okay, so now the receiver knows what it measured, and it knows these decision areas, and it knows how to map those decision areas to the symbols, right? So it has an understanding of the available symbols, but it really has no idea what was actually sent, right? It's just making the best decision it can. Okay, so now here we've drawn a two symbol constellation here, S1 and S2. So these are binary signal, right? There's 2 of these. And we've drawn out the corresponding decision areas, and we have a received vector R here that's been perturbed by noise. Okay, so now we want to understand. So if S1 was sent and we received R, the receivers knows nothing better than to assign that received signal to S1, right? Or to assign I'm sorry. I think I said S1 by mistake. So it's going to associate this receive signal with the transmitted same symbol S2, right? That's all it knows. It's in this decision area 2, so it's going to assign it S2. If it was really S1 that was sent, but this noise perturbed it, then that's going to be an error. And we want to understand the probability, given this constellation, what the probability of that error being. Okay, so we're going to project this vector, vector R here, down to this line that connects S1 to, well, to S2, and it will project onto A right there, right? So, and then we'll compare it to half the distance between these 2 points. D12 would be the distance that we're going to calculate between these constellation points. And then half the distance would mark the boundary of our decision area, right? So we bisect this connecting line normally, orthonormally, right? So so D12 divided by 2 gives us a way to measure this. So we're just saying D12 here is that distance between S1 and S2. So we can look at R here, this vector R, we call this the origin here, then it's S12 plus the noise, right? So you remember way back vector addition, right? So if you start with one vector here, S1, and then you add noise to that, noise is going to have particular direction and amplitude, and you're going to end up, in this case, over here. So R is equal to S1 plus N, noting that we are using a vector representation right now, so we can add vectors. Okay. Now, if we just do the math, then the noise is equal to R minus S1. Okay, so now if we want to get this projection, well, we can do our little dot product operation normalized by that distance there. And so we take this vector S2 minus S1, that gives us this vector here, and we dot that with the noise vector, and then divide or normalize by this distance, then that is a projection of this R onto A, so that's actually the projection of the noise onto A, I'm sorry. So now we can look at the probability of having a bit error, right? So it's binary signaling. So our symbol error, symbols are 1-to-1 for the bits, right? So K is equal to 1. So we can look at our bit probability of receiving the bit in error. So that would be this value here, this projection, this vector projection onto this connecting line would be greater than half of D1 D2, right? So if this is D1 D2 is this distance, half of it would be either this distance or that distance, right? It's the same because it's bisecting. And so if this projection, if n is small, then we would project way over here, well inside the D1 region, right? But the bigger n what n gets, the more it's going to push that resulting vector off into this region. And now when we project it down to this vector between S2 and S1, then as soon as that projection gets more than half of this total distance, or this distance right there, then that would be classified as an error, right? So you got maybe complicated math on this side, but a nice handy diagram on the other side. So try to visualize what's happening and recognizing that this math is due to this vector addition type of thing, and the dot product, right? So we can rearrange terms here and multiply by D12. That's all we've done in this step. And so now we can note that n dotted with S2 minus 1 is a zero mean Gaussian variable with a variance equal to D12 squared times n naught divided by 2. How did I get that? How did I get from here to there? How did I draw these conclusions? Why can I say that n dotted with S2 minus S1 is zero mean? No one wants to hazard a guess? What do we know about the noise? Is the noise zero mean? Yes. That's that additive white Gaussian noise. We're always going to assume that type of noise is zero mean. And that's really all we'll focus on in this course. And S2 minus S1, these are a equiprobable binary signaling. So they're going to, since they're equiprobable, the mean of them is going to also have a zero mean, right? So we've got these two different processes that are dotted together, and that's going to give us a zero mean. So the Gaussian variable here now, the variance describes the power in the signal. So we reference our additive white Gaussian noise as n random process with n naught over 2 by convention. N is going to be some value that really describes the actual power of the noise, but we always refer to n having this variance, n naught over 2. And now we're just looking at that, the amplitude, so of S2 minus S1 would be D12. That energy now would be the square of that, right? So D12 squared. Okay. So that makes life easy for us, as we'll see. So now I'm just repeating the equation there for context. Now we remember back to our Q function, and we're going to see this over and over again. This ends up turning out to be a very important function because of its relationship with Gaussian, and because we are studying the additive white Gaussian noise impact on these communication systems, right? So that's where this origin of why we keep seeing the Q function show up. So This is back to our lecture on the Q function. We said that it can describe the probability of a random variable exceeding some threshold defined by alpha, right? So alpha is a parameter here in the Q function. We subtract out the mean. It's nice when the mean is 0, so we can ignore that. And we divide by sigma, not sigma squared, but sigma right there, right? So now we just look at that and we can plug and chug, right? So what's the probability of this received or this projection of the noise onto this this line here? What's the likelihood that it's greater than this this value here, this D12 squared divided by 2, right? So look at you match up your terms here, right? So alpha would be this D12 squared divided by 2, and the random variable x would be this vector n dot times the vector s2 minus s1. Okay, so now we're just plugging in, recalling that the mean is 0, and so we just have alpha on the numerator, and then on the denominator we have this variance that we observed over here. Okay, and so we just rearrange some terms now and simplify it. And so I think in the previous slide where we note the variance, the D12 is inside the radical, so it shows up as being squared. So sigma squared is D12 squared and not over 2. Sigma is the root of that, so we have square root and not over 2 and just D12. So now we're just going to simplify, rearrange terms. That's just some algebra there, and so that's kind of our result. But what really is this D12 squared, right? So if you think I've been emphasizing that these are vectors all along, so we can use this vector addition and that type of thing, right? But these are really, you know, if we go back to it, these are really signals, right, that exist over some time, minus infinity to plus infinity. Now there's some finite pulse that this information is being sent with, or perhaps it's not finite, but for all intents and purposes it's finite. But we do look to integrate S12 minus S1 of t minus S2 of t, square that and integrate that over time. If we do that and we expand this, then we'll have S1 squared over from minus infinity to infinity. That's its energy, right? And we'll have S2 squared over all time. That's its energy, right? So we can write down the energy S1, the energy of S2. And now as we expand this quadratic here, we'll have minus 2 times this notation here. Do we remember what that notation was? Well, if you go back, it's the inner product from the lecture 4, slide 5. That's when we started talking about this idea of taking these signals that are defined in time and representing them as vectors, right? So now we're going to return to this notation. So the inner product is similar to the dot product. The dot product is a subset of the inner product. So you can, in this case, think of them as the same thing, right? But these are being multiplied together and then integrated over time. And so I'm going to simplify that to say that, well, since these are equiprobable binary signaling, these two energies are going to be the same, right? So S1 is the same distance from the origin as S2, and they're going to be the same, just opposite values in the amplitude domain. But when you look at the energy, they're going to be the same, right? So we can just call both of these E, and then I'm going to write down this notation here, right? So we'll have two of these energies and two of this stuff. So we're going to call this rho. Okay. So now if we look at this, we have D12 squared equals to this 2E representing energy times 1 minus rho. Okay, so rho, what is rho? It's the cross correlation coefficient between the symbols S1 of T and S2 of T. So what does that mean, right? So when we correlate things, we're looking